Good day, everyone. Welcome to EGN 3343. This is thermodynamics, and today we are going to look into thermodynamic cycles for the generation of power using ideal gases or standard gases. Last couple of classes, we've gone over the different types of cycles or thermodynamic power cycles that use vapor as a way of generating power. And today we're going to look at those that use air as a working fluid for this purpose. Now we are going to look at the air standard cycle. What is it? What does it entail? What are the different aspects and arguments to look at when analyzing a thermodynamic cycle that operates on air, and air as an ideal gas. Then we're going to look into particular cycles that are called by the name of their inventor, the Otto cycle, the diesel cycle. We're going to briefly touch upon the dual cycle, but we are not going to implement it. Basically, the dual cycle is a combination of the Otto and the diesel cycle. And then we're going to talk about the Brighton cycle. We're going to do this next class. And the Brighton cycle is slightly different because it is based on open systems. Basically, Otto cycle and diesel cycle are based on closed system analysis, on control masses, because the air, the working fluid, is contained in a piston cylinder assembly. The Brighton cycle, the working fluid actually flows through different open system devices such as turbines, compressors, heat exchangers, and so on. So the Brighton cycle is essentially the equivalent of a Rankine cycle. The Rankine cycle is a vapor power cycle, but it's the equivalent to that when air is used as a working fluid. Now let's look at the air standard cycle. In this case, working fluid is air, and air behaves as an ideal gas. So that's the premise. That's where we depart from. Combustion processes are modeled as heat addition from an external source. So usually what happens in any air cycle or any air standard cycle is that the air is mixed with some sort of fuel, usually a carbohydrate, a fossil fuel. And it's mixed in a proper proportion, and so that the combustion process takes place and is as exact as possible, so that there are no excedents of air or no excedents of the fuel. So that's calculated through a combustion analysis, which is beyond the scope of this class. Now, in the process of burning the fuel with the air as the oxidant to the fuel, there is a heat addition to the system. The air is modeled as acquiring heat from an external source from the thermodynamic point of view, but in reality, the air actually absorbs heat from some sort of an endothermal reaction, which is a combustion process. Now, heat reject process to the surrounding is used to restore working fluid to its initial state. Well, normally, because air is so abundant, what happens is that there's a process during this thermodynamic cycles based on air where air is actually just rejected to the atmosphere. It's just dumped out. Now, these is not modeled this way. Air being rejected out is not modeled as just air rejected out and then new air being acquired and placed into the system. What we do is that from the thermodynamic point of view, we model the process of rejecting the air to the atmosphere as just heat rejection to the surrounding, to restore the air to the original conditions. And the air is indeed restored to the original conditions because in reality it's acquired from the atmosphere. So instead of saying, well, we're going to take that air, dump it to the atmosphere, grab new one, and restart the cycle, we're going to say, well, the air is cleaned up, it's actually cooled down by a heat rejection process, and then the whole cycle starts again. That way we can analyze the whole process as a thermodynamic cycle. And we assume that all processes are internally reversible, and unless otherwise specified, basically that there's some entropy generation or some irreversibilities. So the first thing we want to do is look at the principle of internal combustion engines. What happens in a piston cylinder assembly, and what's the different nomenclature that comes into play in order to analyze the cycles. One is the Otto cycle. One form of internal combustion engine is analyzed under the Otto cycle principle. This is called a spark ignition engine. The Otto cycle is basically the thermodynamic cycle that takes place in all the engines of all your gas powered vehicles. Actually, also the case for natural gas if you go through the conversion of gasoline to natural gas. It's the Otto cycle. And the diesel cycle is a compression ignition engine. It's basically the diesel cycle is a thermodynamic cycle that takes place in diesel engines and engines that use gas oil or diesel fuel as the combustible. And they are called compression ignition engine because the air inside the piston cylinder assembly is actually compressed a lot more than in the Otto cycle, and it's compressed to a point that there's enough temperature generated in the compression process to actually create ignition, or basically to create combustion. That doesn't happen in the Otto cycle. In the Otto cycle, the air is compressed, the air and fuel mixture is compressed, and then there's a spark that actually, at that point, there's a spark that triggers the combustion process. In the diesel cycle, compression takes place at a higher proportion to generate enough temperature so that then you inject the fuel, mix it with the air, and then combustion takes place spontaneously without the trigger of a spark. This is a nomenclature that we're going to be using for piston cylinder assembly, which is where all internal combustion engine processes take place. The bore is basically the diameter of the internal diameter of the cylinder. The piston actually moves from what's called the bottom dead center to the top dead center. There's a few valves, a minimum of 2 valves in the cylinder, one exhaust and one intake valve. There's usually more than that in modern engines. There is a spark plug, the one that triggers the combustion in an Otto cycle, or the one, or just basically an injector to inject the fuel in a diesel cycle. There are a couple of different elements to this process. The bore or the stroke is the same. The bore actually, as I said, the diameter. The stroke is the distance covered by the piston from what's called the bottom dead center to the top dead center. The bottom dead center is the lowest point of motion of the piston, and then the top dead center, obviously, the highest point of motion of the piston. That's what bottom dead center is, and top dead center. The displacement volume is essentially the difference between the volume inside the cylinder when the piston is at the bottom dead center minus the volume in the cylinder when the piston is at the top dead center. So that's what's called the displacement. So when you hear an engine is a 2-liter engine, it's basically that all cylinders in that engine, usually if, let's say we have a 4-cylinder 2-liter engine, that's essentially each cylinder has a displacement of 0.5 liters. Multiply times 4, you have 2 liters. So that's the displacement being the volume, not the distance. So although displacement is a word that relates to distance, in the piston cylinder assembly nomenclature, displacement relates to volume. The compression ratio is a very important factor, a very important number in internal combustion engines, and it's essentially the ratio of the volume in the cylinder when the piston is at the bottom dead center to the volume in the cylinder when the piston is at the top dead center. So that's the compression ratio. As I said, in gasoline engines, the ones which implement the Otto cycle, the compression ratio is less than the compression ratio on diesel engines, because in diesel engines are a compression ignition type of engines. The other important number or parameter to measure in piston cylinder assemblies or in internal combustion engines is the mean effective pressure. And the mean effective pressure, as you know, as this piston goes up and down throughout the thermodynamic cycle, there are different pressures that are developed in the different states. We usually analyze cycles in internal combustion engines that are composed of 4 states. So 4 processes in 4 states. And every one of those states is a different pressure. A pressure changes throughout the process. But there's something called the mean effective pressure, which is essentially a measure of what is the average pressure throughout the entire cycle. And that's equal to the net amount of work or power produced divided by the displacement volume, this VD. Okay. So this is the PV diagram on an internal combustion engine. As you can see, the piston or the volume of the cylinder actually goes from the top dead center to the bottom dead center. And it's called a four-stroke cycle because there's four processes involved. So basically the piston recovers or covers the distance of the displacement, essentially the stroke, 4 times for the process or for the cycle to restart. So this is essentially what happens. The intake process occurs when the intake valve is open. Then the intake valve closes at this point at the bottom dead center, basically when the piston is all the way down. So by absorption, usually, there are some aids to this. Compressors or turbos are used to actually force the air into the cylinder. But in regular aspirated engines, the piston goes down, and as it goes down, the volume of the cylinder increases, and because the intake valve is open, the cylinder is filled with air. Then the intake valve closes, both valves are closed, and then compression takes place. Then the piston goes down, and it goes down to the top dead center. Actually, I'm sorry, the piston goes up, it goes up to the top dead center, and the volume is going down, so the whole thing is compressing. And as it's compressing, basically the temperature is going up. At this point, either a spark is ignites the combustion process, or there's enough temperature for combustion to take place if this is diesel engine or diesel fuel. And then the piston starts going to the bottom dead center and that's the process in which power is generated. From this point, from the top dead center all the way to the bottom dead center again. So the process of expansion is the process in which work is being created. So all that heat that was added during the combustion process is now manifested in an expansion of the volume, in which the piston actually goes down from top dead center to bottom dead center. So once the piston is all the way down, the exhaust valve opens, and then as the piston moves up again to the top dead center, it pushes all the air outside. Now that is not modeled that way from an analysis point of view. We're going to see how we transform this to an equivalent cycle, to an equivalent Otto cycle, or to an equivalent diesel cycle in terms, or for the purpose of analyzing this thermodynamically. So the 4 strokes in an internal combustion engine are usually the intake, compression, power, which is the expansion, and exhaust, as I just explained here in this plot. During the intake stroke, the intake valve opens, the exhaust valve is closed, and the piston moves from the top dead center to the bottom dead center, drawing in mixture of fuel and air. During the compression stroke, intake valve closes, the exhaust valve remains closed, the piston moves from the bottom dead center, from the bottom to the top, by compressing the fuel-air mixture. Near top of stroke, spark ignites fuel-air mixture, causing heat input. Well, that's in the case of an Otto cycle. If it's a diesel cycle, there's no spark. So the compression itself will be enough to actually create the combustion or trigger the combustion. So that's why the fuel is not mixed. In the case of diesel engines, the fuel is not mixed with the air before the compression stage, because otherwise you'll have pre-combustion as the piston is moving up, causing all sorts of problems there in the generation of power. So what you do basically is wait until the piston gets all the way up, and at that point you inject the fuel, try to mix it as homogeneously as possible with the air, and then let combustion take place as the piston is moving down, not as the piston is moving up. The power stroke is the expansion process, is when the piston moves down. Both valves are closed. Hot combustion products expand, causing the piston to move down from the top dead center to the bottom dead center, producing work output. So out of the 4 stages, or the 4 processes, or the 4 strokes of this internal combustion engine, there's only one where power is created. The other 3 are basically either negative power or no power. And the exhaust stroke is with the exhaust valves open. As the piston moves up, it pushes all the combustion gases, all the remnants, pushes it out of the cylinder. The intake valve remains closed. The piston moves from the bottom dead center to the top dead center, forcing spent combustion products out of the cylinder. So therefore, the piston moves the length of the cylinder 4 times for one complete cycle, hence the name 4-stroke cycle or 4-cycle engine. So this is the nomenclature of internal combustion engine, and this is what we're going to base our analysis for both Otto cycles and diesel cycles. Alright, so now let's look at the particularities of the Otto cycle model. How do we take this internal combustion engine principles, the 4-stroke cycle in a piston cylinder assembly, and model all the processes in the cycle to compose what's called the Otto cycle model, and more importantly, how we analyze this from the thermodynamics point of view. Now, the Otto cycle is an air standard thermodynamic power cycle. Intake and exhaust strokes are not modeled, so basically, you, as I said, you model the air as if it was trapped inside the piston cylinder assembly throughout all the processes in the cycle, and then you keep recycling and recycling and recycling, basically restating to the initial state. That's, from the thermodynamics point of view, is equivalent to modeling an exhaust and an intake stroke. So basically, instead of modeling an exhaust, you model heat rejection. Compression is modeled as an isentropic compression. So as the piston moves up and compresses the air, you model that as happening very fast and with no heat dissipation. So there's adiabatic. Heat input is modeled as isometric, occurring exactly at the top dead center. So the process of heat input, which is the process of combustion, usually from the thermodynamic point of view, you conceive this as heat exchange from an external source, basically a hot temperature reservoir, but that's not what happens in an internal combustion engine. There's internal, that's why it's called internal combustion, because there's internal heat addition, because the air is mixed with fuel. So as the air moves, as the piston moves up, the cylinder shrinks, the volume of the cylinder shrinks. That's the compression process. Once the piston is at the top dead center, as the spark plug actually sparks, triggering the combustion, you model that instantly all the heat is actually inputted into the air at that point, exactly instantaneously when the piston is all the way up at the top dead center. So basically you model the heat addition process as an isometric process. It is the process that occurs exactly when the piston is at the top dead center, and that process takes no time, basically, because it's exactly when the piston is there. It's an isometric process, no change in volume. Expansion is also modeled as isentropic, so you assume that there's no heat dissipation. So as the piston goes down and it expands, it's a power stroke. Basically, you assume that there's no heat dissipation. And finally, the heat rejection is modeled as an isometric process occurring exactly when the piston is all the way down on the bottom dead center. So as the piston is all the way down, you assume that the heat is rejected by placing the system in contact with a cold temperature reservoir. That's not in reality what happens. What happens in reality is that you let all the air go, but you model as an instantaneous process, isometric, constant volume. As the volume is down, you reject all that heat. And that, from the thermodynamic point of view, is perfectly equivalent. So in a PV diagram, state number 1 of an Otto cycle starts when the piston is at the bottom dead center, at large volume, at the bottom dead center. The volume of the cylinder is high. Then the compression process is isentropic, adiabatic and reversible, as you can see, isentropic. Then this is the compression stage. No heat, just compression, negative work. From 2 to 3, that's the heat addition process. It's an isometric process. Notice that volume doesn't change, but it's heat addition. Heat is added into the air by combustion instantaneously because there is no change in volume, as you can see. Then from 3 to 4, this is the expansion process. This is a power stroke. It's where power is created. So from 3 to 4, the piston expands, or the piston moves from the top dead center again to the bottom dead center, and it creates power by expanding. And from 4 to 1, this is a heat rejection process, modeled also again as isometric, no change in volume when the piston is all the way down. This can also be seen in a TS diagram exactly the same way. From point 1, which is the point of lowest temperature, this is the beginning of the compression process, you have an isentropic compression, no change in entropy. From 2 to 3, you have an isometric process, no change in volume, that's heat addition. As you can see, entropy goes up, that's heat being added. From 3 to 4, that's an isentropic process, that's a process of creating power, that's a process of expanding. from 3 to 4. And then from 4 to 1, as you can see, this is the process of heat rejection. As entropy goes down, the only way for entropy to go down is by heat rejection. So let's analyze every one of these processes in the Otto cycle. The first process from 1 to 2, this is called the isentropic compression. As you can see in the PV diagram, this is an asymptotic curve with a high slope. Isentropic compression. Q is equal to 0, basically, and reversible. So adiabatic and reversible leads to isentropic process. If we apply the first law of thermodynamics, remember this is a closed system, so we're talking about QW equals to delta U. Because this is modeled as an adiabatic process, Q is equal to 0. So we can calculate the work as just a change in energy. Now, the change in energy is basically U2 minus U1. And because it's minus, we're talking about U1 minus U2. So that's how we calculate the work in the process from 1 to 2. Because it's a compression process, we expect that work to be negative, of course. And also the delta U can be found in tables, so if we use the variable specific heat models, the air tables, or you can use CV times delta T if you assume constant specific heat. Now, because this is an isentropic process, we can relate the properties in state 1 and state 2, namely the temperature from state 1 to state 2, through the VR characteristics, or the VR parameters that are found on the air tables. So we can say that in an isentropic process, VR2 over VR1 is equal to V2 over V1. So it's appropriate to use the VR because we know the ratio of volumes. In a piston cylinder assembly, because the volumes are fixed, you know exactly what the ratio of volumes are from state 1 to state 2. So basically volume 1 is larger than volume 2 by the compression ratio, basically. So V2 over V1 is the inverse of the compression ratio. So that's how you relate VR2 to VR1, through V2 over V1. So let's say in an engine where the compression ratio is equal to 10, for example, which is a typical number in Otto cycles, V1 over V2 is equal to 10, and therefore VR1 over VR2 is equal to 10. So if you know the initial temperature, the temperature at the beginning of the compression stage, which is usually atmospheric temperature, then you can calculate the temperature at state 2 because VR2 is related to VR1 by the compression ratio, and VR2 is basically a function of temperature you can get from the tables. This is assuming the variable specific heat model, which is usually the case. If you assume the constant specific heat model, remember you can relate the properties in an isentropic process by using the relationship P times V to the gamma at state 1 is equal to P times V to the, not the gamma, the K. K is the ratio of specific heats. So P times V to the K is equal to P times V to the K in state 2. The second process is the isometric heating. Isometric combustion, basically. We assume that as the piston is all the way up at the top dead center, piston is all the way up at the lowest volume, top dead center, there's a heating process that occurring through combustion, and that occurs instantaneously with no change in volume. So basically we increase the temperature, increase the pressure and the temperature of the working fluid at constant volume. If we apply the first law, because there is no volume, there is no work. There's no change in volume, there's no work. So we can calculate the amount of heat by the change in energy, or vice versa. We can calculate the change in energy by the amount of heat, if it's a known value. Then the process from 3 to 4 is the power process. It's the process of expansion. It's the process where work is actually created. It's a positive amount of work in the net work calculation. This is also an isentropic process. So Q is equal to 0 and model is internally reversible. If we apply the first law says that because there's no heat, the work is again related to delta U. In this case, it's going to be positive. So minus delta U is expected to be positive. So there is a decrease in temperature from 3 to 4. And as the temperature decreases from 3 to 4, the energy actually decreases. So minus the change in energy leads to a positive number. Because the process from 3 to 4 is isentropic, we can relate the properties in state 3 and state 4 through VRs. Because the ratio of volumes is fixed through the compression ratio from 0.3 to 0.4, volume 3 divided by, or volume 4 divided by volume 3 is equal to the compression ratio. Basically, usually a value of 10 or around 10 in Otto cycles. So then we can calculate, let's say, the temperature at point 4 through the VR at point 4 by knowing the temperature at point 3 through the VR at point 3. Remember that VR is just a parameter that's found in tables that is just a function of temperature. And the final process that closes the loop in an Otto cycle is the heat rejection process that occurs isometrically. It's an isometric cooling from point 4 to point 1. We assumed as the piston is on the bottom dead center, that heat is being rejected isometrically, and because it's an isometric process, W is equal to 0, the work. There's no work in the process from 4 to 1, so we can calculate the amount of heat rejection through the change in energy from 4 to 1, or vice versa. So if we combine all the above equations, there's only one process where heat is added. There's only one process where heat is rejected. The other two processes are adiabatic. There's only one process where work is done on the system. That's a compression process. All the other processes are either isometric or work done by the system. There's only one process where work is done by the system. So this makes the analysis of an Otto cycle very simple. The process from 1 to 2 is a process of work on the system's negative work, U1 minus U2, as we found from the analysis of first law of thermal. The process from 2 to 3 is the heating process. And the heating process is the only process in the cycle where heat is added to the system, and it's U3 minus U2. The process from 3 to 4 is the expansion process, the only process in the cycle where work is actually created by the system, work done by the system, so it's positive, U3 minus U4 from the first law analysis. And the only process in the system where heat is rejected is the process from 4 to 1, and it's calculated, that Q is calculated as U1 minus U4. So the work net, which is the sum of all the works in the system, obviously the work from 2 to 3 is 0, and the work from 4 to 1 is 0. It's just the work from 1 to 2 and the work from 3 to 4. And that's U3 minus U4 plus U1 minus U2. Well, remember, U1 minus U2 is going to end up being negative anyway, so this is in reality a subtraction, because it's a compression process. And the efficiency of an Otto cycle, or the efficiency of any thermodynamic power cycle, is measured as the amount of work produced, net work, divided by the amount of heat that you put into the system. The amount of work that you produce is this net work, U3 minus U4 plus U1 minus U2, divided by the Q that's added to the system. This is the cost of creating power. This is the cost of fuel, basically, U3 minus U2 in this case. And that will give you the relationship for the calculation of the efficiency of an Otto cycle. So let's look at an example of an Otto cycle implementation. We are told that at the beginning of the compression process, at state number 1, in an air standard Otto cycle, the pressure is 14.7 psi and the temperature is 530 Rankins. Okay, that's usually the case at the beginning of the compression stage. This is the air that comes into the cylinder from the atmosphere, so that's why it has atmospheric pressure and nearly atmospheric temperature. And this is 430 Rankine is 70 Fahrenheit, so it's essentially atmospheric temperature and pressure. We're going to be working this problem in British units or U.S. customary units, just for the purpose of just exercising this, although you should not expect this to be the case in the homework assignments or in the exams. The compression ratio is 8. That means that the ratio of volumes from when the piston is at the bottom dead center to when the piston is at the top dead center is 8. That's slightly low compression ratio. This is probably maybe a low compression ratio engine, an older engine. If we're told that the maximum cycle temperature, which is usually the temperature, or it is the temperature at the end of the combustion process, 0.3 in the cycle, we are to determine the Carnot efficiency, the thermal efficiency, and the mean effective pressure. Now, the Carnot efficiency is just the calculation that is done for a point of comparison, so that we know for a fact that the thermal efficiency that we calculate cannot surpass ever the Carnot efficiency. The Carnot efficiency is the highest limit for efficiency under this particular conditions. If the thermal efficiency we calculate goes above the Carnot efficiency that we calculate, then we have a problem. We violated the second law of thermodynamics. And we're also to calculate the mean effective pressure. So let's look at the summary conditions. We're going to be calculating pressure, temperature, specific volume, energy. We know we need all the energies in the system to calculate the efficiency. And we are going to be calculating or finding in tables that value of VR, VR being that is sometimes referred to as a relative volume, but it's not a relative volume, it's just a function of temperature that is related somehow to volume. It's a unique function, it's an exclusive function of temperature, so if you have the temperature you can get VR from the tables, and we're going to use it because of the isentropic process. It's only meaningful in isentropic processes. So we have pressure and temperature at the start of compression, that's point 1, and we know the temperature at the end of expansion. It's 2000 Rankine. And we know the compression ratio, which is the ratio of volumes from 1 to 2, and the ratio of volumes from 4 to 3 is equal to 8. So if we calculate the volume at 1, we should have enough information to be able to calculate all the volumes in the system, because the volume at 2 is 1/8 of the volume at 1. The volume at 3 is the same as the volume at 2, because this is an isometric process from 2 to 3, the heating process. And the volume at 4 should be the same as the volume at 1. Now, it will be very easy to calculate the volume at 1 because it's just the application of the equation of state. We can go to the tables. From the tables, we can find information about, because we know the temperature at state 1 and we know the temperature at state 3. We go to the tables, and I'm not going to show you snapshots of the tables because these are tables in British units. You can find them in your textbook or you can find them online. But at 530 Rankine, we can find that the energy of air is 90.3 BTU per pound, and the VR, or relative volume, is 151.38. At 2000 Rankine, the energy of air, the internal energy of air, is 367.61 BTU pound, and the VR is 4.258. So let's see how we use this information. This is by using the air tables. First of all, these are the equations we have. Because air is an ideal gas, we use the equation of state, P times V equals to RT. First law of thermodynamics, Q minus W equals to delta U. For isentropic processes, we know that V1 over V2 is equal to R, and that is the same as VR1 over VR2, so we can relate the temperature that way from 1 to 2. We also know that 3 to 4 is an isentropic process, so V4 over V3 is equal to R, and therefore VR4 over VR3 is also equal to R, and that is something that we can use to relate the temperatures between state 3 and state 4. The efficiency is W net over Qn, and the mean effective pressure is the W net over the change in volumes from 1 to 2, basically the displacement. All right, let's start with the solution. We said that because air is an ideal gas, we can use the equation of state. It says that P times V is equal to RT. Let's solve for the specific volume at state number 1. The gas constant for air in British units is 53.3 pound-force feet over pounds degree Rankine. The temperature at 1 is 530 degree Rankine, and the pressure at 1 was given as 14.7 psi, or pound-force over square inches. So we have to convert the square inches to square feet. Remember that 1 square foot is 144 square inches, and that leads to an initial specific volume of 13.35 cubic feet over pound, which is the inverse of the density in British units, essentially, at atmospheric conditions of 530 Rankine and 14.7 psi. Then we know for a fact that the volume at state 2 is 1/8 of that, because from 1 to 2 the piston goes up, and it goes up by a factor of 8. So basically the volume at state 2 is 13.35 divided by 8, so the specific volume at point 2 is 1.68. Basically the specific volume goes down, the density goes up. So in the process from 1 to 2, the new volume is 1.67. Now VR2 is also related to VR1 because the process from 1 to 2 is isentropic. Only because the process from 1 to 2 is isentropic. VR1 being found on the table at 530 Rankine, 151.38. We divide that by 8. So the VR2 The relative volume at point 2 is 18.92. And since that is a function of temperature only, we can go to the table and find temperature 2 and also the energy in state 2. So now we know that the VR2 is 18.92. This is part of the solution process. We go back to the table. We found the volume at state 2 is 1.67. We found the VR at state 2 is 18.92. And then we go to the tables with that 18.92 for VR and find the temperature and find the U. Remember that the ideal gas tables, more importantly or specifically the tables for air, are just organized by temperature. Temperature is the only entry. So energy, enthalpy, entropy, or entropy zero, VR and PR are only functions of temperature. So if we have VR, we can go back and get the temperature, and we can go back and get the energy. So that's how we complete column number 2, the conditions at state 2. Now, we could take this temperature and this volume, put it back in the equation of state, and calculate the pressure of state 2 if necessary. It might not be necessary, so let's move on and look at state number 3. Now, in state number 3, we already have the temperature. We already have energy and VR directly out of the tables. So, and we know that the volume at state 3 is the same as the volume at state 2 because the process from 2 to 3 is isometric. So, let's look at the solution of the problem from 3 to 4. We know that the volume at 3 is equal to the volume at 2. It's 1.67. And we know that the volume at 4 is equal to the volume at 1, or basically 8 times the volume at 3. And in an Otto cycle, the processes move basically between two volumes. And in this case, it would be between the initial volume of 13.35 to the second volume of 1.67. Now, V4 over V3 is equal to 8. And therefore, BR4 over VR3 is also going to be equal to 8. So the relationship between VR4 and VR3 is through the compression ratio. We know VR3, we found it on the table, is 4.258 when we multiply that times 8, and it's only true because the process from 3 to 4 is isentropic. The only reason why we can do this is because the process from 3 to 4 is isentropic. That's the only time when the relationship of the VRs holds true. VR3 over VR4 is equal to V3 over V4, and we know that's equal to 1/8. So VR4 is equal to 34.064, and we can use that value to find T4 and U4. Remember again that the table of air is organized by temperature only. So if we know VR, we will know temperature, energy, enthalpy, and whatever we need. We go back to the table. Notice the volume. I copied volume 1 at 0.4, 13.35. We know that the relationship of volumes holds true also for the relationship of VR. So VR3, which we found at 2000 Rankine, is multiplied by 8, 34.064. Then with that value, we get the temperature from the table. We interpolate at 954, and we get the energy from the table, 164.2. So that's basically the completed table. Again, we can use these temperatures and these volumes to calculate all these pressures if we want to, but the pressures are no longer necessary for any type of calculations. We have everything we need, the temperatures and the energies. The temperatures to calculate the Carnot efficiency, the energies to calculate essentially the thermal efficiency. And then, furthermore, we have the volumes and the energies to calculate the work net, and the volumes to calculate the displacement, and the ratio of the two of the mean effective pressure. So let's look at the calculations. Basically, work on the system is the work from 1 to 2, which is minus the change in energy per first law analysis. 90 minus 207 is minus 117.03 BTU pound. As expected, it's negative because it's a compression process. From 2 to 3 is an isometric process. So as expected, obviously no work. Q is equal to delta U. As expected, that will be positive. 160.28 BTU per pound of heat added to the system. From 3 to 4, there's work done by the system. That's the expansion process, because there's no Q, because it's an adiabatic process. Work is equal to minus delta U from the first law analysis, and it's equal to 203.41, positive as expected. And from 4 to 1 is the process that closes the cycle, is a heat rejection process, Q is equal to delta U from 4 to 1, which is U1 minus U4. It's minus 73.9 BTU per pound rejected energy, as you can see, negative. Now let's use all these numbers to make our calculations. First of all, the efficiency of Carnot is 1 minus the coldest divided by the hottest temperature in the system. O is an absolute temperature. We have that. The coldest temperature is 530. The highest temperature is 2000. The efficiency of Carnot is 0.74 or 74%. That's the highest limit for efficiency in this particular cycle under these conditions. If we find that the thermal efficiency is larger than that number, we violated the second law of thermodynamics. So let's calculate the actual thermal efficiency, which is the net work divided by Qn. The net work is work by minus work on, or basically work by plus work on, but work on is already negative. So the net work generated in this process, or in this cycle, is 86.38, and we put in 160 BTU per pound of energy in the combustion process. That's 0.54 or 54%. That's the efficiency of the cycle. And because it's lower than the Carnot efficiency, it respects or it follows the second law of thermodynamics. This efficiency is assuming that the processes are internally reversible, that there are no losses in the process from in the expansion process or in the compression process. These are assumed to be perfectly isentropic. That might not necessarily be the case, but in this case we're not being specified if there are any losses due to irreversibilities. Furthermore, we can calculate the mean effective pressure as the average pressure in the system. The only pressure we know, we didn't bother calculating pressure at 2, 3, and 4, although we could have done that by using the equation of state. But the only pressure we know is 14.7, which is the initial pressure. We know that pressure is going to go up in all the other processes from 1 to 2, and from 2 to 3, and then from 3 to 4 it goes down. But the average pressure or mean effective pressure is the net work divided by the change in volume. And we're going to do this in specific format because we don't have an idea, we don't have information about how much mass is in the cylinder. If we knew how much mass there was, we can calculate the total work, not the specific work. The net work, again, is work by minus work on, which is 86.38 BTU pound. 86.38 BTU pound we transform into pound force times feet by the conversion of 778 pound force feet over a BTU, because we want that pressure in PSI basically. And the volumes change from 1.67 to 13.35. That is the displacement, but that's the displacement in specific volume. If we multiply that by the mass, we get the actual displacement in volume. And we transform the square inches to square pound, or the square foot to square inches. One of these feet will go with this feet in the pound force feet, and we'll end up with pound force over square inches, which is essentially PSI. So the average pressure in the system is 39.9 PSI, starting from a pressure of 14.7. If you actually put a manometer on the cylinder, you manage to put a manometer on the cylinder throughout the entire process or throughout the entire cycle with functioning engine, it happens so fast that you won't see the 14.7 and the high pressure and the low pressure. It happens so fast that the needle will actually clock at 39.9 basically at all times. So this is the analysis of a standard Otto cycle, in this case ideal, under ideal conditions. Alright, so let's look now at the diesel cycle model. It's very similar to the analysis of Otto cycles. That's why we study one right after the other. Remember that the diesel is a compression ignition engine. Basically, you compress a lot more than an Otto cycle, and you compress to a point where there's enough temperature to actually spark the combustion, so you don't need a spark plug. You don't need to trigger with a spark. It is also an air standard cycle. Intake and exhaust strokes are not modeled. Same thing as in the Otto cycle. Compression is modeled as isentropic, the same exact thing as in the Otto cycle. So from initial condition 1 to condition 2, we model that as a compression, as an isentropic, adiabatic reversible compression. The heat input, however, is modeled slightly different. The heat input is modeled as an isobaric process. So instead of modeling the heat input instantaneously at top dead center. We model as the piston goes up, you inject the fuel, and then obviously the piston is going to go down a distance, and we call that distance the cutoff. Okay, so there's a distance throughout where the piston goes down that you model that as the heat addition process. So instead of modeling the heat addition or the combustion process as perfectly isometric, instantaneous, you model the combustion process as isobaric. As the piston is going down, combustion is taking place. And it occurs from the top dead center to a cutoff volume. Okay, not all the way down, but through an intermediate volume between the top dead center and the bottom dead center. The expansion is modeled as isentropic, same way it is done in in the Otto cycle. But notice that in this case, both the heat addition process, the combustion process, and the expansion process are positive work type of processes. In both cases, the air is expanding, piston is going down. So there's two processes in which work is being created: the process from 2 to 3 and the process from 3 to 4. And finally, the heat rejection process is modeled as isometric, the same exact way as it is modeled in an Otto cycle. As the piston is all the way down in the bottom dead center, you model heat rejection. These are the PV and TS diagrams of a diesel engine. As you can see, from 1 to 2, we have the same thing, isentropic compression. Now from 2 to 3, instead of this line being vertical, isometric, now it's isobaric. Okay, so there is an expansion, and it's an expansion to an intermediate volume between the top dead center and the bottom dead center. It's called the cutoff volume. This is the process of heat addition. This is Qn. From 3 to 4, we have an isentropic expansion, so more work being created. In this case, adiabatically, combustion has completely stopped at point 3, and from point 3 to point 4, it's just inertial type of expansion. And from 4 to 1, you have the isometric heat rejection. So this is exactly the same as the Otto cycle, except from process 2 to 3, which is, instead of being vertical, is horizontal. And this is a conversion to a TS diagram. The only difference is the process from 2 to 3 has a slightly smaller slope than before, because instead of being an isometric process, it's an isobaric process. Well, let's analyze every one of these processes. Process from 1 to 2 is an isentropic compression. Isentropic compression from 1 to 2. Same way we analyze it from the Otto cycle. The isentropic compression means that there's no heat, so therefore we can calculate the work as a change in energy, or negative of the change in energy from 1 to 2. Same thing we did before. Now the volume is moving from bottom dead center to top dead center through the compression ratio, which is usually higher in diesel engines. So because this process is isentropic, we can relate the volumes from 1 to 2 to the VRs from 1 to 2, which are functions of temperature, through the compression ratio. Okay, same thing we did for Otto cycle. The only difference in the diesel analysis is the process from 2 to 3. The combustion process occurs isobarically instead of isometrically. So now, applying the first law entails that we are not going to be able to say that the work is equal to 0, because basically there's work being created from 2 to 3. There's positive work by the system. There's expansion. So Q from 2 to 3 minus W from 2 to 3 is equal to delta U. We know that because the pressure is equal to constant, the work is simply pressure of 2 and of 3, which is the same, times V3 minus V2. And it's expected to be positive. And as we plug this back into the first law of thermo, we notice that when we add PV to delta U, we get delta H. So we can calculate Q from 2 to 3 as delta H, or simply work plus delta U. Same thing. Okay, this is a result of adding PV to delta U. We get directly delta H. Okay, now the relationship between the volumes from 3 to 2 is done by what's called the cutoff ratio. The cutoff ratio is that ratio of volumes of where the piston goes, as the piston is going down, is the cutoff of the injection, the fuel injection actually being turned off. So there is a stage from the top dead center all the way down to a cutoff volume through which combustion takes place. And at that point, at the cutoff volume, you cut combustion by cutting the intake or cutting the the fuel injection. So basically that cutoff ratio called RC is the ratio of volumes V3 to V2. And it's obviously a number larger than 1. It's the ratio of volumes throughout which combustion takes place. The process from 3 to 4 is identical to the process from 3 to 4 in the Otto engine. It's an isentropic expansion. It's work creation. It's a power stroke. In that process, there's no heat because this model is isentropic. So work from 3 to 4 is delta U from 3 to 4. So another work. So there's work created from 2 to 3 and there's work created from 3 to 4. But since delta S is equal to 0, we can relate the volume 4 to volume 3 to the temperature 4 and the temperature 3 through the VRs. Now, V4 over V3 is no longer the compression ratio. It's a compression ratio, but it's less than the compression ratio. The compression ratio is V1 over V2. V4 over V3 is exactly the compression ratio divided by the cutoff ratio. Okay, so V4 over V3 is the compression ratio, all the volume from 1 to 2, divided by the compression ratio, by the cutoff ratio, RC. Normally the compression ratio on a diesel engine is 15 or above, and the cutoff ratio is something around 2 or 3. It's the ratio of volumes throughout which combustion takes place. And that is the relationships of the volume between 0.4 and 0.3. And you can relate those through the temperatures by using the VRs in the tables. Now, if you're using the constant specific heat model, this is an isentropic process, so you can say P times V to the K at 0.3 is equal to P times V to the K at 0.4. And the final process, the process that closes the cycle, is a process from 4 to 1, is an isometric cooling. It is identical to the process from 4 to 1 in an Otto cycle. Because it's isometric, there is no work. And because there's no work, the amount of heat rejected is equal to the delta U. Okay? And volumes are equal to each other, and 4 and 1. So let's combine all these equations to notice that the work done on the system is only from 1 to 2. That's the only compression process in the system, is minus delta U. There's only one heat addition process, and that is the process from 2 to 3. And as we found from the first law analysis, it's a change in enthalpy from 3 to 4, no longer the change in energy, because there's a volume change from 2 to 3. The work done by the system, it happens on the process from 2 to 3, from top dead center to cutoff, and from cutoff to bottom dead center. So from 2 to 3 is isobaric, and from 3 to 4 is isentropic. Okay, and there's only one heat rejection process, and it occurs from 4 to 1, and it's equal to delta U. The net amount of work is the sum of all the works. From 2 to 3 is P times V3 minus V2. From 3 to 4 is U3 minus U4. And from 1 to 2 is a compression. This is going to end up being negative, is U1 minus U2. The efficiency is the work net divided by the heat addition. This is the work net as we define it, as we found through the first law analysis. And the heating process, the combustion process occurring at constant pressure, is H3 minus H2. So when we analyze diesel engines, we have to incorporate, or diesel cycles, we have to incorporate not only the calculation of energies in the tables, but also we have to find the enthalpies in the table, at least the enthalpy in 0.3 and in 0.2, to be able to calculate these things. All right, so now let's analyze a diesel cycle using the formulations that we just came up with. In this case, we have an air standard diesel cycle with a compression ratio of 16, which is a number that you'll find usually in diesel analysis. So very large compression ratio. Then a cutoff ratio of 2. That means that as the piston gets up to the top dead center, the volume multiplies by 2. It duplicates, it doubles from top dead center to a cutoff volume by a ratio of 2. We're told that at the beginning of the compression, the piston, the air inside the cylinder is 14.2 psi, that's atmospheric pressure, and the temperature is 520 Rankine, that's 60 Fahrenheit, that's also atmospheric pressure. So this is at some sort of elevation, as you can see, because it's low pressure, low atmospheric pressure. We're talking about maybe some city where there's some elevation. The temperature is also 60 Fahrenheit. So, And we're told that the volume 1, total volume, is 0.5 cubic feet. Total volume, that's the total volume at bottom dead center, 0.1. We are to calculate the heat added, the heat rejected, the Carnot efficiency, the thermal efficiency, and the mean effective pressure. So let's see. This is what we have on the table. In this case, we only have one point defined, as opposed to in the Otto cycle analysis, where you usually have to know the temperature or something else at the end of the combustion process. In this case, we have 14.2 psi of pressure at state 1 and 520 Rankine. So we can use the state equation to calculate the specific volume. Right? We are given the full volume, which is 0.5 cubic feet, but we can calculate the specific volume through the state equation, or the mass through the state equation. We know we added enthalpy to the table because we know we're going to need a state 2 and a state 3 to calculate the efficiency, or the heat in, or heat added to the air. And VR. We know the compression ratio, which is the volume 1 over volume 2, is 16, and the cutoff ratio, which is V3 over V2, is equal to 2. We are going to go to the table. From table, knowing the temperature state 1, we can calculate energy, enthalpy, and VR directly out of the table. Well, I didn't look up the enthalpy because it's not necessary at state 1. We only need the enthalpy at state 2 and at state 3. But we could do so very easily. These are the equations. As you can see, same equations as we had before. Air is an ideal gas, so PV is equal RT. First law of thermodynamics, we've already implemented that and found all the relationships for all the processes in the system. The efficiency, thermodynamic efficiency of the entire cycle is work net divided by Qn. And the mean effective pressure is always work net divided by the change in volume, the total change in volume, the displacement. Not the cutoff, but the displacement. For the two isentropic processes in the cycle, process from 1 to 2 is an isentropic compression. V1 over V2 is equal to R, and therefore VR1 over VR2 is equal to R as well, so we can relate the temperatures that way. And the other isentropic process is the expansion from 3 to 4. Where V4 over V3 is compression ratio over cutoff ratio, and that also applies to VR4 over VR3. So V4 over V3 is equal to 16 over 2, is equal to 8, and VR4 over VR3 is also then equal to 8. As part of the solution, since we know temperature and pressure at state 1, we can calculate the volume, the specific volume, through the state equation. We know the absolute volume, but we don't know the specific volume. We can relate those two and calculate the mass. But the gas constant for air, temperature 520, and pressure is 14.2. Remember the conversion from square inches to square foot, so we can get the volume in cubic foot, or divided by pound mass. So it's 13.56 this time. Now, knowing the volume at state 2, we can divide that by 16, which is the compression ratio, to find the volume at state 2. The volume at state 1 is 13.56, and the volume at state 2 is 0.8475. Using the same compression ratio of 16, we can relate VR1 to VR2, because the process from 1 to 2 is an isentropic process. From the table, we found that VR1 was equal to 158.58. We divide by the compression ratio 16, and we get a VR2 equals to 9.911. So knowing the VR at state 2, we can go back and find the temperature, the energy, the enthalpy, and whatever we need, because the tables are organized by temperature. So here it is. With a VR of 9.911, that's the only thing we know in state 2, we can go back to the table, calculate temperature from the table, 1502, interpolate the energy, 266, and interpolate the enthalpy, 369. Now the volume we found as 1/16 of the initial volume. Now we can go from 2 to 3. We know that the volume doubles from 2 to 3 because the cutoff ratio is equal to 2. So we can use that volume, double the volume. We know that the pressure is the same from 2 to 3, okay, because the process from 2 to 3 is an isobaric process. So we need to calculate the pressure in 2, equate that to the pressure in 3. Then with the pressure and the volume, we can calculate the temperature. And knowing the temperature, we can go to the table and calculate U, H, and VR. Okay, so that seems like a simple process. So let's see. The pressure in 2, using the equation of state, same thing, RT over V. Remember the conversion from square foot to square inches, and that leads to a pressure at point 3 of 656 pound-force per inches. The pressure at state 2 is equal to the pressure at state 3 because the process from 2 to 3 is isobaric in a diesel engine only. So, because of the compression of 16, we go from 14.2 psi to 656 psi in state 2 and in state 3. Now the volume at state 3 is the cutoff times the volume at state 2. The volume increases from 2 to 3 by a factor of 2. So the volume at point 3 is 1.695 cubic feet per pound. So now we know the volume at 3 and we know the pressure at 3. With the volume at 3 and the pressure at 3, we can calculate the temperature at state 3. Using the equation of state, T3 is equal to P3V3 over R. P3 is 656. V3 is 1.695. The conversion between square inches and square foot is 144, so that we can get rid of the square foot here and the volume. And the R is 53.3 pound-force feet over pound mass Rankine. That leads to a temperature 3 after the combustion process of 3,000 Rankine. So it's a very large temperature that diesel engines see. So, knowing the temperature of 3005, we can calculate the energy and the enthalpy as needed, and also the VR from the tables. So we go to the table with 3005. Notice the pressure is the same as pressure in 2. Volume is double than the volume in 2. But what's important is the temperature, because with the temperature we can go to the table and calculate the energy, the enthalpy, and the VR. Okay, so now we have almost everything solved except for point 4. Now point 4, remember, is related to point 3 through an isentropic process. The entropy from 3 is equal to the entropy from 4. And because that's the case, we can relate, for example, the volume from 3 to 4 as a ratio of the VRs from 3 to 4. We know that the volume from 3 goes to the volume of 4 by R over RC, or basically the volume of 4 will be exactly the same as the volume of 1 because the process from 4 to 1 is isometric. So the volume at 4 will be 13.56, which is exactly 8 times the volume at 3. Remember, the volume from 2 to 3 doubled, and now the volume from 3 to 4 is going to go up 8 times. So the volume at 4 is 13.56. The ratio of these volumes is equal to the ratio of VRs because the process from 3 to 4 is isentropic, and therefore VR4 is going to be 8 times VR3. So let's see. V4, let's go back. V4 is equal to V1, 13.56, or 8 times V3. The volume 4 over volume 3 is equal to 8, is the compression ratio over the cutoff ratio, or 13.56 over 1. Whatever the value of V3 was. So we can relate the VR4 to the VR3 to the same factor because the process from 4 to 3 or from 3 to 4 is isentropic. So VR4 is equal to VR3 times 8. VR3 we found in the tables to be 1.174 times 8 is 9.39. So now we have the VR at point 8, at point 4, 9.39. With that value, we go back to the table, get T4, get U4, and H if we need it, but we don't need the H at point 4. So with a VR of 9.39, we can find the temperature from the tables, 1531, the volume we already found, and the energy is state 4, 272. If we need it, we could find the pressure at point 4 because we know the temperature and the volume through the state equation. But we might not need that. We can calculate the mass of at any point. Well, we know the volume at state 1, which is 0.5, and we know the specific volume, which is 13.56. Remember that absolute volume is mass times specific volume. So we can calculate mass as absolute volume over specific volume, 0.0369 pounds. Okay? So with the mass, not only we can calculate the specific works and the specific values of heat added and heat rejected, but if we multiply by the mass, we can calculate the total values in BTUs. So now we have all the energies in the system and the two enthalpies we need to calculate everything. So Qn is the enthalpy change from 2 to 3, which is after we implemented the first law of thermodynamics. That's 422.75 BTU pound. Qn is therefore mass times Qn. The mass is 0.0369 pounds times that value is 15.6 BTU. So there's an addition of energy to the air of 15.6 BTU due to combustion in the isobaric process from 2 to 3, but that happens at every stroke of the cycle, or at one of the strokes in the 4-stroke cycle. And remember that this happens very often, because if, let's say, the engine is rotating at 3600 RPM, it's rotating 60 times per second, so basically this occurs 60 times in a second. So there's a lot of heat addition that's the cost of fuel. The Q out, the heat rejection, occurs from process 4 to 1. That's the isometric process, so Q out is equal to U1 minus U4. That's minus 183.78 BTU per pound. So Q out is equal to mass times Q out, and that's equal to minus 6.78 BTU. So it's negative as expected. So there's a combustion heat addition of 15.6 and a heat rejection of minus 6.78. And finally, we can calculate the work net. We can calculate the work net by adding all the works in the process. The positive work is from 2 to 3 and from 3 to 4. The negative work from 1 to 2. Or, because this is a cycle, we can calculate the work net as equal to the Q net. So let's see. The work net is equal to the Q net because this is a cycle. Okay? All the sum of all the works in the system are equal to all the sums of all the Q's in the systems. And the work net is equal to Q in minus Q out, which is 15.6 minus 6.78 BTU. So the net amount of work is 8.82 BTU. That's the net amount of work produced in this cycle. It's Q in minus Q out. The efficiency of Carnot, because there's a very large change in temperatures because of the high compression ratio, is 0.827, so 82.7%. That's the limit of efficiency due to Carnot. So the thermal efficiency that we find should be less than that number in order to respect the second law of thermodynamics. The thermal efficiency is the net work divided by Qn. It's 8.82 divided by 15.6. It's 56.4%. So no, as you can see, efficiencies on diesel engines are higher than efficiencies on auto engines or gas engines. And it's due because of the large compression ratio, the large change in temperature. And the limit is also higher, it's 82.7% limitation of Carnot efficiency. So, finally, we can calculate the mean effective pressure as the net amount of work divided by the displacement volume. The displacement is volume 1 from minus volume 2. Volume 1 is 0.5, and volume 2 is that divided by 16. The volume goes down by a factor of 16. So, basically, the displacement volume is around 0.45 cubic feet, and we divide 8.82 by that. We use the factor of 778 pound-force feet over BTU, and we use the factor of 144 square inches per square foot in order to have the mean effective pressure in PSI. And the mean effective pressure that we find for this particular case is 101 PSI. So the average pressure in a diesel engine is also much higher than the average pressure in an auto engine. In the example we worked out for an auto cycle, the mean effective pressure was 39.9. And now the mean effective pressure for these diesel engine, especially starting from the same condition, is 101 pound-force. It's more than twice, actually, 2.5 times that pressure as in the auto cycle. So this is it for the analysis of internal combustion engines. We are not going to touch upon the dual cycle. The dual cycle is basically a combination of the auto cycle and the diesel cycle. But this actually gives you at least an introduction to how you apply thermodynamic principles of the first law of thermo and the second law of thermo to power cycles that use air in closed systems in a piston cylinder assembly. Next class, we'll analyze power cycles in open systems, so basically the Brayton cycle, which is the equivalent of a Rankine cycle, but when the working fluid is air. So thank you for your attention, and I'll see you next class.